Hello everyone, welcome back to the fourth installment, I believe, of my calculus series. Today we'll be going over the chain rule for differentiation. So we've already been through what differentiation actually is via the first principles. We've done the product rule for polynomials and some trig differentiation. So now we're going to go to the chain rule. So just to jump right in, what is the chain rule? Well, the chain rule tells us that the derivative of y with respect to x equals the derivative of y with respect to some other parameter t multiplied by the derivative of t over with respect to x. Now be careful, these are not fractions, so although it looks like you can just multiply them and then cancel out the dt's, that's not how this works, and any maths teacher will kill you if you do this, so try not to. But it works for nearly everything that you do at sort of A level, so it doesn't really matter too much. So what does this rule actually tell us? Well, it's immensely useful because let's say we want to find the derivative of something like, I don't know, 2x squared all to the fifth power. Well, this is not what your average polynomial looks like unless you expand it, which why would you? And it's, let's make it a little harder. And this also does not look like anything else we've done. So this is where the chain rule comes in. The chain rule tells us that the derivative of this equals the derivative of the outside multiplied by the derivative of the inside. So what does that mean? Well, let's just treat this 2x squared plus 1 as a single variable. Let's call it a. Well, let a equal 2x squared plus 1. This means that what we're trying to find is, so this becomes 3a to the fifth power. So if we want to differentiate this, we have to differentiate with respect to a. So dy over dA, so d over dA, that's going to give us a dy over dA, which is going to equal, we can just use the product rule here for polynomials, 15a to the 4. Then we take this a equals 2x squared plus 1. So if we try to take the derivative with respect to x, that will give us dA over dx, which equals 4x. So now we can use this rule. So we can take dy over dA, 15 a to the 4, and a, if you remember, is just 2x squared plus 1 to the fourth power multiplied by dA over dx, which is 4x. And that is our answer. And it's quite useful because we can use this essentially for anything that's embedded, any kind of function like that. A function inside a function, really, that kind of thing. We can use it for a whole host of stuff. It's very useful. Probably one of the most useful things in differentiation outside of maybe the first principle, I'd say.